Multiple time series is more general in real world, and which means that detecting entity-level anomalies is more important than metric-level anomalies. Although detecting anomalies at the entity level is more intuitive, it has following challenges. First of all, the labels of real data are rare. It's difficult to train a classifier. Moreover, in some real scenarios, such as pipeline monitoring, we need to process detected anomalies to prevent occurrence of dangerous accidents. The business applications or monitoring system must process millions, even billions of time series in near real time. The anomaly detection procedure needs to be finished within limited time. Since different devices will generate various kinds of time series, the detection model should work well on different patterns. Finally, an anomaly may be caused by several metrics. It's important to show the root cause of the anomalies to help operators better understand the incident. To address those challenges, we propose adversarial autoencoder, anomaly detection and interpretation, namely DMIN, and online unsupervised anomaly detection and interpretation framework. Specifically, AMA framework mainly contains three components: data pre-processing, offline training, and online detection. First, we introduce the data pre-processing module. Recent study shows that spectral residual algorithm performs well on univariate time series anomaly detection. We import the spectral residual to clean data and then normalize data with min-max normalization. Next, we present the offline training module. First, we introduce the network structure of the detection model. As illustrated in the figure, the network structure of DMIN consists of three parts: an autoencoder, including an encoder and a decoder, and two discriminators. Given a time series, the encoder generates a posterior distribution and a hidden variable. We design an adversarial network to guide the posterior to match a prior distribution. And then the decoder generates the reconstruction of the input. Another adversarial network is proposed to avoid overfitting, which compares the difference of the statistics between original and reconstructed time series. For the four networks, we use the one-dimensional convolutional neural network with filters sliding along the temporal dimension as the basic network structure. The training process is shown in the figure, since there are two discriminators in our model. The encoder and the autoencoder can be regarded as two corresponding generators. We can train our model by a two-player min-max game. In each iteration, two discriminators are trained for key steps. One discriminator is used to guide the posterior distribution to match a prior distribution. At the same time, the corresponding generator tries to compute the discriminator. Another discriminator is trained in a similar way. Next, we present the online detection module. The online detection module consists of anomaly score computation, threshold selection, and anomaly interpretation. After the training process, we can use the DMIN model to determine whether a new entity is anomalous or not. Since the historical entity are beneficial to understand the pattern of an entity, we take the sequence as the input to reconstruct the entity, and the reconstruction error is used to compute the anomaly score of the entity. After computing the anomaly score, the anomaly score will be sent to threshold selection module to recognize whether the entity is anomalous or not. Specifically, for each entity, we mention a window, namely correlation window, which contains the anomaly score of a historical entity associated with the current entity, and compute the mean and the standard deviation of the correlation window. For a new entity, we first compute its anomaly score using the detection model. And then the anomaly score is compared with the mean and the standard deviation. If the anomaly score of the current entity exceeds the confidence interval, the entity is anomalous. Next, we present the anomaly interpretation module. Motivated by the integrated gradients method, we analyze the anomaly interpretation by integrating the gradients for each dimension of an anomalous entity. The practical step of applying integrated gradients in our anomaly detection program is to select a suitable neutral baseline entity. When selecting a neutral baseline entity, we can compute the deviation between the input and the neutral baseline entity by the autoencoder. Since the reconstruction of the input data is crucial to determine whether the input is anomalous or not, we use the reconstruction as the neutral baseline entity of an anomaly. Given an anomaly entity and its corresponding neutral baseline entity, the deviation computed by the autoencoder between them is the sum of the deviation of each dimension. Since anomalous dimensions deviation significantly from normal dimensions, the deviation of each dimension can be used to analyze the root cause of the anomaly. Dimensions with larger gradients deviation are more likely to be the root cause of the anomaly. Next, we show the experimental results. We conduct experiments on 4 real-time series datasets. We use 4 metrics to measure the performance of all algorithms. The performance is evaluated in 4 aspects: effectiveness, model variance, threshold selection, and anomaly interpretation. For effectiveness of all algorithms, DIM outperforms all baselines on most of the datasets, and its FP score is only slightly lower than the best baseline on SMAP dataset. Moreover, DIM shows the best performance on the FP score on total dataset compared with the other state-of-the-art methods. The robustness of DIM is better than that of all baselines, since the processing and recall values of DIM are both higher than 89% on all datasets, which cannot be achieved by any baseline. For the model variance, we reconfigure DIM to create 5 variants, as shown in the figure. DIM outperforms variance on most of the datasets. Since the SMAP dataset is routine, there is no dramatic change in the pattern of the data, resulting in the best performance of using LSTM. For the effectiveness of adaptive correlation window, we compared it with the peaks over threshold approach. Since in real applications, the number of monitored time series is nominal, making it infeasible to maintain a correlation window for each entity. To overcome the limitation, we adopt a simple but effective strategy by using the validation set as the correlation window for each entity in the testing set. From the table, we can see that FP score obtained through adaptive correlation window is slightly lower than the best FP value, which performs better than peaks over threshold. Since the weight of different luminous dimensions is various, we propose a new anomaly interpretation metric, normalized reconstructed discounted cumulative gain, namely NRDCG. First, we rank the top k dimensions. Both gradients contribute most to the anomaly as the root cause. And then, for a dimension which is in the ground truth, we compute its distance, measuring how far it is from the ground truth to a same value in our ranking list. Moreover, we normalize the RDCG for all approaches. An RDCG decreases with the increase of P, because more items of ground truth can be included in the ranking list, needing larger RDCG and its ideal value. While the value of the ideal value of RDCG changes greater than itself, the performance of DIM is better than that of other state-of-the-art methods, regardless of P, which demonstrates the superiority of our proposed interpretation approach. Finally, we conclude our work. We propose a new architecture for multivariate time series anomaly detection, which design an intuitive and effective way to recognize anomalies and an anomaly interpretation approach. The extensive experiments based on real-world datasets confirm our proposed framework performs better in time series anomaly detection and interpretation. That's all for my presentation. Thank you for your listening.